Uh, Thank you for the introduction. My name is Jesse Moody, and I'm presenting a passive 461 megahertz aluminum nitride CMOS RF front-end for event-driven wake-up receivers. I'm presenting this paper on behalf of Pouyan Bassirian, who is not able to make it today. Going on to the application space for event-driven wake-up receivers. The idea is to enable a technology known as smart sensor nodes, which essentially integrate ultra-low power analog front-ends with low-power digital back-ends to enable some continuous monitoring of some ambient stimuli in the environment. These stimuli could be, as we've seen earlier today, chemical, vibrational, or thermal, or a whole host of other mechanisms. So one very important aspect of this technology is battery lifetime. As people are talking about a trillion nodes on the internet, if you want to change a trillion batteries, that's going to be quite difficult. So minimizing standby power consumption is a very important aspect of the IoT research. So some applications enabled by event-driven wake-up receivers would be smart cities, where basically everything in your life is monitored by machines, agricultural monitoring, as well as unattended ground sensor networks for military and defense applications, as well as security, of course. So on to the RF front-end requirements for these detectors. So the principal metric that you care about in these types of sensors is DC power consumption, much more so than most other radio applications. So we've adopted a detector-first architecture, essentially foregoing the use of any oscillator or heterodyne type of receiver. Instead, just going with a completely passive front end, where we achieve all of our voltage boost passively. This is because it requires a lot of power to bias your transistors into a regime where they can get sufficient, FTs, Fmaxes to provide power amplification. So what we've done instead is used a impedance matching network for all of our voltage gain, and as well as our input filtering. The reason I mention input filtering especially is because the envelope detectors in CMOS are extremely wideband, and that's an issue if you're considering interferers. Whereas, for instance, our envelope detector has similar responsivity at 50 megahertz as it does 1 gigahertz. So a signal at 915 megahertz getting through our detector is gonna cause us some issues. So some solutions for this impedance matching network would be lumped element networks, which have inherently low Qs. These can actually provide, from what we've seen so far, superior voltage gain, but they don't provide sufficient filtering to reject most out-of-band interferers. Another alternative would be RF MEMS filters. These are ultra high Q and very selective, but they have weak capacitive drive strength, meaning you attach a 200 femtofarad capacitance, it'll destroy the performance of the filter. So ideally, we want the performance of both the lumped element and the MEMS filters. So naturally, our solution was a hybrid RF MEMS lumped element filter, where we integrated a lumped element filter with a MEMS resonator, as well as a CMOS RF front end to make an RF front end for an event-driven wake-up receiver. This allowed us to use the ultra high Q of the MEMS resonator in our filter, and thereby improved our performance against lumped element filters. Going on to the integration was accomplished on a Rogers 4350 PCB, and we did this because essentially, as I said, we're using an impedance matching network for all of our voltage gain. So the impedances that we're transforming up to are in the tens of kilo ohm range. So any shunt resistance, in this case, this is the ESR of the equivalent capacitance on those interface nodes, actually has a significant impact on the performance of the circuit. So that's why we went with the low loss Rogers material. Here we have a process flow for the aluminum nitride resonator, where it was fabricated on a high resistivity silicon substrate and made out of the aluminum nitride for this particular design. Onto the hybrid matching network design. Primarily, the first stage of the lumped element filter was used to resonate out the input capacitance of the detector, which is on the order of picofarads for the for our original phase 1 chips. Then the acoustic matching, the MEMS element was used to provide a reel-to-reel impedance transform, as well as provide series high Q filtering, and finally the last stage just resonated out the last of the capacitance at that to provide a 50 ohm match. And we can see that the input impedance versus frequency of the resonator is very, very sharp. So it only really passes signals at that very narrow resonance. Onto the envelope detector design and integration. So we went with a 32-stage Dixon envelope detector. So this type of detector requires really careful design of both the RF response and the baseband response of the detector, where careful design at the RF frequencies ensures high sensitivity. Careful design at the baseband frequencies ensures that you have a fast transient response. One critical aspect of the interface between these two components is minimization of the parasitic capacitance, where you can see from this plot right here in the right-hand side of the slide that our output signal-to-noise ratio drops significantly with increasing parasitic capacitance at the interface node. Onto the input impedance transformer performance. So this is both simulated and measured. So what we did is we did a one-port VNA measurement of the acoustic resonator, and then we fitted that into models of high-accuracy models of the lumped elements. And we saw that we had a simulated voltage gain of about 10 volts per volt with this transformer. With the envelope detector, again, a one-port VNA measurement with very high levels of attenuation, because this it's a detector working in the quadratic regime, so large signal levels induce third and higher order nonlinearities, changing the input impedance slightly. So you really need to. It's actually surprisingly difficult to do the input impedance measurements for this type of detector. And then we did the voltage sensitivity as a function of input power with a key-side source signal generator. Onto the integrated RF front-end measurements, we saw that the front end up to the output of the detector had a voltage gain of about 9 volts per volt versus an open circuit input, and that we saw we had a minus 10 dB bandwidth of about 20 megahertz. Integrating this into a larger system, which primarily just consisted of a digital comparator as well as on-chip clock source, not including any additional correlation, we were able to see a high sensitivity of about minus 58 dBm, where our false positive rate was at a rate that we could easily filter out with even a low 8-bit correlator. We can easily filter out that false positive rate down to less than once per hour. And the total back-end DC power consumption was less than 8 nanowatts. In conclusion, we saw that careful co-design of the MEMS resonator and the lumped element filter allows for you to take advantage of both elements and allows you to achieve a high Q filter with very high voltage gain. And finally, careful co-design of the RF and the RF CMOS and the MEMS and the lumped elements is crucial for achieving a successful Wakeup receiver. Finally, I'd like to acknowledge all the support we've had from the Integrated Electromagnetic Circuits and Systems lab from UVA, the Robust Low Power VLSI lab from UVA, particularly Abhishek Roy for system level demonstration and primarily on the design of the digital backend, and finally Troy Olson of DARPA for support. Thank you.